Down, and it's now recording. So let me, I think I'll hold off the share screen for a moment and let you know just a couple things that are happening, because you may get concerned, and hopefully you won't, but in case you do. We have to go out of town this weekend. This is going to be the biggest we've gone out of town since this whole COVID stuff started. But we have I grew up on a farm in Georgia, and after both parents died, the farm was split among the four of us, and my two brothers continued operating it as a farm for a while. They got tired of taking care of the cattle and the equipment and the not row crops, the grains and stuff like this. So it was pretty labor intensive. They're both getting older, so they decided to sell the herds, sell the equipment, and plant pine trees. So that's the whole farm pretty much, except my older brother kept one field without trees in it. But the rest of the farm is all in trees. But my wife and I decided on our part to put in about 400 hardwoods instead of pines. And hardwoods, well, they're a little more expensive. You have a little bit more invested, in fact, quite a bit more invested in them. But they also need a little more TLC. And that's what we've got to do this weekend. We've had such a rainy spring and early summer that the grass is just about, it's pretty tall around the trees, and that's sucking moisture around them. Well, we've had a wet spring, so there's been plenty to share, but July and August can be very hot and could be dry months. So we wanted to get the grasses pushed back and to give the trees a little more opportunity to do well. So we're going over to mow and to spray chemical on the grasses near the trees, but not hit the trees because that would kill them. So it's going to be a tedious weekend. It's going to be a long weekend. It's going to be a tiring weekend. The reason for saying all this, if you've sent anything in recently and you haven't seen me acknowledge it yet, I've got about 45 minutes after this class. I'm going to eat lunch too. About 45 minutes before I have two advising appointments. And then after those are over, I've got, I think, 2 hours before my next class. So sometime in that 2 hour and 45 minutes, I'm going to try to print out anything you may have sent in and get as much graded as I can. But once tonight hits, we're going to be packing to get ready to go. And my wife, being the infectious disease epidemiologist that she is, we are leaving as early as we possibly can in the morning. So basically the car has to be packed tonight except for the perishables, and those will be loaded and in the car early as we can in the morning. We're going to hit the road because she figures if we do have to stop, which we will have to stop and at least get gas, she wants to get there as early as possible so as fewer people could have been in the service station before us as possible. Now, this is going to be over in Madison, Georgia, so they're going to have plenty of opportunity, but we're not going there at the end of the day when there's just been a whole herd of people. Hopefully, we'll get there before, if there is any virus spreading around, we hope to, and we'll have our mask on and all like this and use our hand washing and all that. But we're trying to minimize risk. Then we're going to work tomorrow afternoon, all day Saturday. Unfortunately, we'll probably have to work some on Sunday as well. But we're not going to come back on Sunday because same type deal. Everybody else would have been coming back on Sunday, and we might be better chance of exposure. So we're going to leave as early as we can conceivably leave on Monday morning to try to be back before my 11:30 class on Monday. Which, the bottom line for that is, I may not have any time to do any grading, and the DSL line over there is so terrible, I may not be able to get on the internet at all. So if something doesn't get done by the end of the day today, it probably won't get done until sometime Tuesday afternoon, because I have classes all Monday, late morning into the evening, and then Tuesday morning 8:30 up until this class is over with. So don't be expecting to see things being completed grading in that time frame. And if you send me emails, I may or may not see them, just because things are going to be crazy and not going to be in good internet contact. So that's my announcement. I hope y'all don't have anything that complicated going on. But anyway, any questions? Well, I think that we allowed enough time for anyone to get here, so let's go on and start with the whiteboard. And what I'm going to do now is move this taskbar down out of the way. If y'all see anyone or sense that anyone's trying to get into class, please let me know. And I'm going to move this taskbar out of the way on the upper end, and then I'll move your beautiful names here over against the side, and we'll go from there. All right, any questions? Can y'all, all of you see the taskbar? I mean the whiteboard. All right.
Yeah.
Now my memory was we ended Tuesday on Chapter 2, Matrices, Section 2.2, Properties of Matrix Operations, and we had been talking about matrix multiplication and the various properties of that, and that's what Example 3 is going to be doing. So here is Example 3, page 54 in your text if you've got your text. Now, Leah, do you have a text yet?
Yes, I have the PDF.
Oh, excellent, excellent. Okay, and James, you already have one. Okay, and okay, so let's go from there. Matrix A is this 2 by 2 matrix, 1, -2. Now, we didn't do this one. It seems like I wrote this down last time. Is this where we stopped? And 2, -1.
Yes, sir. We had just started working on that problem.
Okay, but we didn't get it finished. Is that right?
No, sir.
Okay. All right. So I thought that sounded awfully familiar. Matrix B is going to be this one. One, 0, 2. And 3, -2, 1. Okay, matrix C is going to be -1, 0, 3, 1, and 2, 4. Sorry, this is so painstaking to watch me write. Now, what we're going to be investigating to see if indeed their statement earlier that in a sense, as long as the matrices are sized properly, that the product of AB, that's a pretty ugly A, multiplied times matrix C, if it can be done, to see if indeed we come up with the same answer as when we associate it differently. So let's do what they're saying here. Let's first multiply A times B. Now, I'm not going to write them again because they're in the right order up here, and there they are, but you tell me the answer to the first question is it even possible to multiply these two matrices? What's the size of A?
2 by 2.
What's the size of B?
2 by 3.
Okay, so 2 by 2, can you multiply that by, if I can write my 2 in, by a 2 by 3?
Yes.
Okay, the answer is yes. What will be the size of the product? You can do it, and the reason is this last number here is a 2, the number of columns of A is a 2, the number of rows of B is a 2, so yes, you can multiply. What will be your product answer?
2 by 3.
2 by 3, perfect. Now, you don't have to do this, but I kind of like to do it, and that will be 3 columns and 2 rows. So I'll just put blanks there to represent where I know the answers are going to be. Now, what's the address of this one? First row, first column. So what we're going to do is take the first row of the first one, A, and multiply it by the first column of B, multiplying and then adding as we go. So 1 times 1 is 1, plus negative 2 times 3 is negative 6. So what does that add to?
Negative 5.
Negative 5. Perfect. All right. This happens to be first row, second column. So we take the first row of A again, but this time multiply it by the second column of B. So that's a 1 times a 0, 0, plus a negative 2 times a negative 2. What does that give us?
4.
Positive 4. Perfect. This address is the first row of first row, third column. So we take the first row of A times the third column of B and see what we get. 1 times 2 is 2, plus a negative 2 times 1 is
Negative 2.
negative 2, and that adds to be a
0.
0. All right, go down to the next space. This is in the second row, first column. So we take the second row of A, first column of B, and multiply and add as you go. 2 times 1 is
2.
2, minus 1 times 3 is
Negative 3.
negative 3, so that gives you a
Negative 1.
negative 1. Perfect. Next place here is second row, second column. So we do the second row of A times the second column of B. That's going to be a 2 times 0. Of course, it's 0. Minus 1 times a minus 2 is
2.
plus 2. Okay? And then the last position here is second row, third column. So we take the second row of A, third column of B. 2 times 2 is
4.
4. Minus 1 is
3.
3. Okay. So that's your product of A times B. Now we want to multiply that, if we can, by C. I'll write down C then because it's so far away. Minus 1, 0. Three, 1. That's an ugly 3. And a 2, 4. Okay. When you multiply those two together, first, can you multiply those two together? This one's a 2 by 3. What's this one?
By 2.
3 by 2. And can you multiply those? My pen won't write. It's just sticking right where it wants to stick. Okay, there we go. By 2. Can you multiply those two? Yes, you can, because the inner dimensions are the same. Rows of A, the product of AB is equal to the columns of C. So you can multiply, and what size will you get at the end?
2 by 2.
2 by 2. Okay. So I like to do this. You don't have to if you don't want to. Okay. First entry here. First row by first column. So first row of A multiplied by the first column of B, or C, I'm sorry, the first row of the product AB by the first column of C, and add as you go. -5 times -1 is 5, plus 4 times 3 is 12. That's 17 plus 0. Thank you for that 0. 17 is top, big enough for me. Okay, so that's 17. Next is the first row, second column. That'll be the first row of the product times the second column of C. -5 times 0, 0. 4 times 1 is 4, plus 0. So that should come out just being a 4. Agreed? Okay. Second row, first column would be second row of the product, first column of C. That would be a -1 times -1 is +1, plus 6. That would be 7, plus 6 again. I think that's going to be a 13. Do you? Or did I do it wrong?
I'm a little confused about how you multiply that one, Dr. Fowler.
Oh, okay. I may have been going too fast.
Well,
Yeah.
I thought I had it at first, and then it threw me off when you multiplied 4 by 3.
Okay, wait. Okay. Which are you doing? The entry down here, 2, 1 entry, or the one up here, the 1, 2 entry?
Yeah, the 1, 2 entry.
1, 2 entry. Okay, I may have done it wrong. Let's see. That's the first row here by the second column here, right?
Yes, sir.
-5 times 0, 0. +4 times 1, 4.
4.
And then 0 times 4 is...
Okay.
Yeah.
So you do that. You do -5, 4, and 0. And you do it by all of those numbers.
Yeah. You do this one by that one, plus this one by that one, plus this one by that one.
Okay.
Yeah.
I think I was trying to multiply this row by the -5 and -1 by -1 and 0. Yeah, I was multiplying it wrong.
Okay. Got it right now?
Yes, sir. I see what you're saying.
Okay. Do we need to do 2, 1 again?
No, sir. I get it now.
You got it?
Yes,
okay.
sir.
You too, Aaliyah?
Yes.
Okay. So the final one is the 2, 2 entry here. Second row, second column. So let's do the second row of the product times the second column of C. So -1 times 0 is
0.
0. 2 times 1 is
2.
2. 0 plus 2 is 2. And 3 times 4 is 12. And 2 is 14. Now that's what I got. Let's see what the book got. 17:4, 13:14. Got it. But we haven't verified to see if that's the same as A times BC. So let's first do BC. Let's try to do it here. B is a 2 by 3. C is a 3 by 2. So sure enough, we can multiply them, and that'll give us a 2 by 2, right? So BC we're going to do down here. I'll label it here. BC. And we just determined it's going to be a 2 by 2. Sort of a big old fat 2 by 2 here. 2 columns and 2 rows. Okay, so let's multiply those two together. B times C. First entry here is the 1, 1 entry. So we'll take the first row of B times the first column of C. First row of B by the first column of C. And let's multiply. 1 times -1 is?
-1.
-1 plus 0 times 3 is 0. So it's still a -1 plus 2 times 2 is 4. So that's a -1 plus 4 is a
-3.
Plus 4. -1 plus 4.
Oh, yeah, plus.
Yeah, we're adding those. Okay. All right. Now, the 1, 2 entry will be the first row of B times the first column of C. So 1 times 0 is 0. 0 times 1 is 0. So you're left with this just being 2 times 4 is 8. Okay? Ooh, that's going to be ugly, I can tell. That is really ugly. Let's see if we can clean that up a little bit. It's so ugly, there's no hope for it. Okay, so let's go back and try that again. I'm going to leave the line off now because that was hard to get it to fit. Okay, I think that's an 8. All right, now the 2, 1 entry here will be second row of B times the first column of C. 3 times a -1 is?
-3.
-3 plus a -2 times a 3 is?
-6.
-6. So -3 and -6 gets us up to -9 plus 2. That, I think, is going to be a -7. Perfect. Okay. And then the last entry is the second row, second column. So second row of B times second column of C. 3 times 0 is?
0.
-2 times 1?
-2.
Plus 1 times 4 is?
+2.
+2. Perfect. Okay. And we're going to multiply that by A. A is 1 -2. Two -1. Okay. Can you multiply those two?
Yes, sir.
Because they're each 2 by 2, meaning the product is going to be a
2 by 2.
2 by 2. So let's 2 columns, 2 rows. Okay? And let's start. 1 times 3.
3.
Plus a -2 times -7. What does that come out?
It's 17.
Yeah, total of 17. Okay, perfect.
I was going to let somebody else answer.
You were just looking at the one above and saying it's better be the same, didn't you? Yeah, that I know you. Okay. This is the 1, 2 entry here, so it's the first row of A again times the second column of the product. So that's be 1 times 8 is 8 minus 2 times 2 is 4. And 8 minus 4 is
4.
4. Perfect. The 2, 1 entry will be the second row of A times the first column of B. 2 times 3 is 6 plus 1 times 7, or minus 1 times -7 is 7. 6 plus 7 is
13.
13. It's looking good. And then the 2, 2 entry will be the second row of A times the second column of the product. And that would be 2 times 8 is 16. Minus 2 would be
14.
14. There we have it. Exactly identically the same. Okay. Now that doesn't prove it, but it does verify that it's true, at least in that case. And indeed it is true. All right. Now, Any questions on example 3? All right, to go to example 4. Clear the drawing. Yay? Okay. Now, here are two matrices. A is another 2 by 2. And it's going to be 1, 3, 2, negative 1. 1, 3, 2, negative 1. Okay. B is going to be another 2 by 2 matrix. And that's going to be 2, negative 1, 0, 2. 2, negative 1, 0, 2. All right. Now what they want us to do is to investigate what the product of A times B is. That's not going to be too bad, is it? So A, product of A times B, what size will it be?
2 by 2.
2 by 2. So we'll draw in 2 columns and 2 rows and go to town with it. Okay? The 1 entry here will be the first row of A times the first column of B. And that will be what?
1 times 2
Is
2.
2 plus
3 times 0 is 0.
So that gives you a 2. The 1, 2 entry here will be first row of A, second column of B, and that will be a
negative 1
negative 1,
plus 6,
which comes out being
5.
5. Perfect. The 2, 1 entry here, second row of A, first column of B will be
4 minus 0.
Okay, so that's just 4. And then the 2, 2 entry will be second row of A, second column of B, and that will be
negative 2 plus a negative 2, be negative 4.
negative 4, if I could write. That's a negative 4. All right, we want to investigate that and compare it to B times A. And since
Can you do the calculation a little slower?
okay, sure. You want me to go back over any of those?
Yes, like how did you multiply A and B?
Okay. All right. Let's go back and do it a little bit more slow. No, this is your second class. So, and we're
yeah.
Okay. So get this first entry here, which is the 1, 1 entry. First row, first column. You do the first row of A times the first column of B. Multiplying the elements, adding the sum, the products. So it's 1 times 2 is 2 plus 3 times 0, 0. So that would just be 2. Do you see that?
Yes.
Okay. Now, what's the address of this entry here, where we have a 5? It's the first row, second column, right? So we go up here to the first row of A, second column of B, and we multiply those, adding as we go. Excuse me just a minute. I need to... Sorry. Excuse me. It got a little stuffy in the room earlier, so I turned on the ceiling fan. It's not that warm, so I got a little tickle in my nose. Okay, so where were we? First row of A, second column of B. Okay, that would be 1 times a negative 1 is
is -1.
-1 plus 3 times 2,
6.
6.
Yeah.
-1 plus 6 is plus 5. Okay. Want to do the next one?
Okay. It'll be row 2.
Right.
2. Right?
Yeah, row 2 times column 1. Exactly.
Oh, okay. So it'll be 2 times 2 is 4.
Right.
And -1 times 0.
Yeah, is.
Oh, it's gonna be 0.
Yeah. So see, plus 4. Right? Got it?
Thank you.
Okay. You want to do the next one? Are you okay?
Okay.
All right. Good deal. All right, no problem. Be sure to ask. Okay. Now, since we're going to do BA, I want to write A over again so it'll be in the right location. Otherwise, I get pulled backwards if I do it otherwise. So, whoa, that's not what I wanted to do. Oh, I didn't know I could do that. I'm having fun. Okay, never mind. Okay. A is 1, 3, and 2, -1. Now, my first question, as usual, is, can we even do that? 2 by 2 times a 2 by 2. The rows of B is equal to the columns of A. I'm sorry, I said it backward. Columns of B is equal to rows of A. So yes, we can, and the result will be a 2 by 2. So BA will also be a 2 by 2. That's encouraging. We know they're the same size. The question is, are they going to be the same values? Let's see. We said it's going to be a 2 by 2, so that'll be 2 columns and 2 rows. Okay, first entry here, first row, first column, so we'll do the first row of B times the first column of A, adding as we go. So 2 times 1 is 2, minus 1 times 2 is minus 2, 2 minus 2 is 0. Uh-oh, SpaghettiOs, this isn't working out, is it? Well, let's do the next entry. First row times the second column, so that will be 2 times 3, 6, plus the -1 times -1 is 1. 6 plus 1 is 7. Even worse. Well, the 2, 1 entry, second row of B, first column of A, that would be 1 times 0, 0, plus 2 times 2 is 4. Well, we finally got one entry, right? But that wasn't required. That was just happenstance. And then the 2, 2 entry here, second row of B, second column of A, would be 0 times 3 is 0, minus 2. No way! AB is not, in general, ever BA. Now, there's sometimes you can't even get them to size up right, and you can't even do the multiplication. But even when you can do the multiplication, most of the time they're not going to be the same. There is at least one very notable exception, and we'll get to that in a little bit. Not yet. Okay, but generally AB is not equal to BA. Okay, and we got, let's see if they got the right answers. They had 2, 5, 4, -4, and 0, 7, 4, -2. Yeah, we got them right, or they did one. Okay, now here's what they say. Do not conclude from example 4 that the matrix products AB and BA are never equal. They sometimes are. But those are usually very special matrices. Okay? And here's what they say to do next. I'm going to use what I can of what we had before, and oh, let's just clear it out of the way, okay? Oh, let's not, okay, because it's too tedious to write. Let's do what we can. A is 1, 3. Oh, that, no, it isn't. Is 1, 2. So I'm going to change the 3 to a 2. I'll do that later. 1, 1. So I'll change this. If I can change, there we go, and change the minus. Well, I thought it would be easy to do. There we go. B is negative 2, 4. Well, I thought this was going to be easier to do, okay? And 2, negative 2. Okay. So we'll leave that alone. We'll change that one. We'll change that one. We'll change that. That. Well, there we go. And let's just change everything here. Oops, more than I wanted to. Okay. Sometimes the thing sticks and sometimes it doesn't. All right, let's go back to the drawing board. And A was 1, 2.
Dr. Fowler,
Yes.
are we trying to arrange it so that we can have an equal answer?
They're saying this will be.
Okay.
We're not trying to do it. The book's saying it, but we'll let them get away with it. Okay?
Okay. Yes, sir.
All right. 1, 2, 1, 1. That's the A. And a negative 2. 1. No, negative 2, 4. I was really lazy. 2, negative 2. Okay. And then I'll repeat A again like we did before. 1, 2, 1, 1. All right. And just because the sizes stayed the same, we know we can multiply them, so let's do them. I happen to accidentally erase a couple of bars here. Okay. So let's do AB. First entry, the 1, 1 entry, first row, first column. Do first row of A times first column of B. What would that be? 1 times negative 2 is negative 2, plus 2 times 2 is 4. High level math now. And negative 2 plus 4 is 2. All right. First row, second column will be first row of A, second column of B. That would be 1 times 4 is 4, plus 2 times negative 2 is negative 4. 4 plus negative 4 is 0. All right. Second row, first column, second row of A, first column of B will be 1 times negative 2 is negative 2 plus 2, that's a 0 again. Okay? And then the 2 entry here will be second row here, second column there. 1 times 4 is 4, minus 2 is 2. Okay, there's AB. Now let's do the similar stuff with BA. B's the same, and I rewrote A, so it's the same. But we'll do the 1 entry here, which would be first column of B times the first row of A. It'd be negative 2 times 1, negative 2 plus 4 would be a 2. Hey, so far, the same. Now let's do the 1, 2 entry here. First row of B, second column of A. It would be negative 2 times 2 is negative 4 plus 4 times 1 is plus 4. Oh man, that adds to a 0. 2 out of 4. All right. Let's go down here to the second row, first column, second row of B, first column of A. 2 times 1 is 2, minus 2 times 1 is minus 2. That adds to 0. 3 out of 4. Can we make it all 4? Let's see. The 2 entry here would be second row here, second column there, and that will be 2 times 2 is 4, minus 2 times 1 is minus 2, 4 minus 2, look at that, it's a 2, okay? Now, few and far between will you find two matrices that, when you multiply them together, commute the multiplication, you'll get the same answer. But I'm willing almost to make you a bet that every time you do, now I'm trying to recall, haven't we introduced the concept of the identity matrix? James, you probably would know. Aaliyah, that was before you came into class.
Yes, sir.
We did. The identity matrix is the matrix is one down the main diagonal, that's from upper left to lower right. They all have to be square, by the way. Identity matrices are always square, okay? Ones down the main diagonal, zeros everywhere else. Guess what? This is a multiple of an identity matrix, and my contention is, I want to say every time, but in the vast majority of the cases, when you have this property that the multiplication commutes, you're going to find out the products will be a multiple of the identity matrix, just like this is. This is twice the identity matrix. Now, that's not done in the book. I'm just telling you that's my take on it. Now, another important quality of matrix multiplication, matrix algebra, let me bring the book over, is that it does not have a general cancellation property for matrix multiplication. So in other words, if you know that matrix A times matrix C happens to be equal to matrix B times matrix C, and of course the C's are the same, does that mean A is equal to B? Matrix A is equal to matrix B. Maybe sometimes they are, but usually they're not, okay? It is not necessarily true that A is equal to B. And this will be a demonstration of that. Now, there are some matrices that it will be valid for, but not in general. So let's do example 5. Okay? Now, I'm going to, I think I'll erase the screen. Is that okay? Though these are all 2x2s, I don't know. I think it's easy to erase. Any question? Okay. So let's go with matrix A, B, and C. This is example 5, bottom of page 55. Here's matrix A. Okay, it's 1, 3, 0, 1. Okay, matrix B. Is 2, 4, 2, 3. Okay, matrix C. is 1, negative 2. Negative 1, 2. Okay. That's so tedious. Okay. Let's first do the product, for some reason, of A times C. Just remember what we're doing. A times C, not A times B. A times C. Can you do that matrix multiplication?
Yes, sir.
2 by 2 times 2 by 2 is going to be a 2 by 2. So that's going to be blank, 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 blank. 2 by 2. Something there. Okay? So A times C. First row, first column, first row of A times first column of C. That would be 1 times 1, 1, plus a 3 times a negative 1, that would be a negative 3. 1 minus 3 is
Negative 2.
negative 2. Got it. The 1, 2 entry would be the first row of A, second column of C. So that's going to be 1 times negative 2 is
Negative 2.
negative 2, plus 3 times 2.
6.
So negative, yeah, that's a 4. Okay, done. Now the 2, 1 entry will be second row of A times first column of C. That's going to be a 0 times 1 is
0.
0, plus a 1 times a minus 1, that's going to be a
Minus 1.
negative 1. Excuse me, my throat's getting incredibly dry, I think. Those almonds tasted good, and I needed a little energy. They were a bit too dry on the throat. Okay. And then the 2, 2 entry here will be second row of A times the second column of C. And again, 0 times negative 2 is
0.
plus 1 times 2 is 2.
2.
All right. That wasn't too bad, if I could write. Okay. Now the next thing we're going to look at is B times C. B, C. First, can you do that?
Yes, sir.
Sure you can. And what size will it be?
2 by 2.
2 by 2. So, let's put in the blanks. Blank, 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 blank. Doesn't mean I was cursing or anything. Okay, now, the 1, 1 entry, first row here, first column here, would be the first row of B times the first column of C. 2 times 1 is
2.
2, plus 4 times a minus 1 is
Negative 2.
negative 2. Perfect. 2 minus 4 is negative 2. The 1, 2 entry here, again, first row of B, second column of C. That will be 2 times minus 2 is negative 4, plus 4 times 2 is 8. So minus 4 plus 8 would be
4.
4. Hey, looking pretty familiar, isn't it? The 2, 1 entry here would be second row of B, first column of C. 2 times 1, 2, minus 3 times a plus the 3 times a minus 1 would be minus 3. That gives you a -1. Look at that. And then the 2 entry here would be second row here by second column there. That would be a 2 times a -2, -4 plus 3 times 2 is 6. That would be a 2. Oh my goodness, look at that. AC is exactly identically equal to BC. Now the C's are the same. Does that mean A is equal to B?
So,
What do you think? You know, A is nowhere close to B. In fact, they don't even have a single element in common, and yet their products with C are both the same. So no, just because you have AC equal BC, you can't divide out the C's. Doesn't work that way with matrix multiplication. It does with numeric multiplication. You can do that. You cannot do it with matrix multiplication. Don't even try. Okay. Now, you'll now look at a special type of square matrix that has 1 on its main diagonals and zeros elsewhere. Oh, have we heard that before? That's called the identity matrix. And since you weren't here before, I'll write it all out again, Aaliyah. And here is in general what it is. This is called the I sub n. It's the identity matrix. And identity matrices are always square. Now, when I do square, I usually use this symbol here. Now, that has a special significance to me. When I was growing up, I had an older brother and a younger brother. Still do, by the way. Okay? My older brother was fairly introverted, fairly quiet. We were only 2 years apart. We were good friends. Okay? We got along really well just about all the time. I guess we had a few squabbles or squats, but basically got along really well. He was a pretty good student. I always tried to beat him because I came along later and I could set my heights higher. And so I think he got a little irritated with that because he did well, but I always tried to do better because I just wanted to, I don't know. Anyway, along came the third brother. He was 3 years younger than me, actually closer to 3.5 years or more. So he was a little more distant. And by the way, I was big. My older brother was a little small for his age, so we were almost always about the same size. Somewhere along the way, I actually passed him, okay? But we were almost like we were closer than 2 years. Dan, though, was about average for his age, but that was quite a bit smaller than the two of us. So he didn't even try to compete with us. He tried to do a lot of things with us, but he didn't compete with us. And he just decided he'd be the wild child, okay? We moved and other things were going on. He was Mr. Extrovert. Mike and I were pretty much introverts, okay? So as we continued getting older, I stayed pretty staid, you might say, kind of rule bound, okay? Dan was anything but. He was the wild child, okay? So after a while, he started calling me L7, which makes a square, okay? And literally, he called me L7. In fact, after a few years or months or so, whatever, he just changed it to L. And even to this day, every now and then he'll say, hey, L, okay? So when I make it square, I do it as an L7 because that was my name, okay? I was considered by my younger brother to be a square, which I guess there's worse things you could be considered, but it wasn't particularly appreciated at the time. Okay, but anyway, here is what we call the identity matrix, okay? Like I said, in the main diagonal, okay, that's starting from upper left corner, it's a 1. And everything else in the first row, is going to be a 0. Okay? And remember, identity matrices are always square. That's why we don't put but one subscript. It's an n by n. Same number of rows, same number of columns. In the second row, the first entry's got to be a 0 because that's not on the diagonal. But the next entry, the 2-2 entry, will be a 1. And then everything else in the second row is going to be a 0. Only the diagonal elements are 1. In the third row, first entry is a 0 because that's not a diagonal element. Second entry is a 0 because that's not a diagonal element. But the third one, 1-1, the 3-3, is going to be a diagonal. It's going to be a 1 because it's a diagonal element. Everything else in the third row is going to be a 0. And it continues. And let's just do a dot, dot, dot down here. And in the last row, it's going to be a 0 there. Okay? This one will dot, 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 and be a 0 here. This one will be a 0 here with a dot, dot, 0. And all of them continue this way except that very last one. All these, well, I should have just put a dot, dot, dot. And these are all dot, dot, dot. Until next to the last row is a 0. But then the last one's a 1 because that's on the diagonal. All these on the diagonals, dot, 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 are 1s, and everything else are 0s. 0s everywhere except that main diagonal. That's your identity matrix. I sub 3 would be 1, 0, 0, 0, 1, 0, 0, 0, 1. In fact, that's it right up there. This 3 by 3 right here. Okay? I sub 17 would be 1 with 16 zeros, a 0, 1 with 15 zeros, a 0, 0, 1 with 14 zeros, and on until you get 16 zeros and a 1. Okay? 2 by 2, 1, 0, 0, 1. That's it right there. Okay? And a 1 by 1 is just going to be a 1 because it's only a diagonal element. Okay. So that's your identity matrix. They list 3 of them there. The I sub 1 is the element 1. I sub 2, as I pointed out, was 1, 0, 0, 1. And I sub 3 was 1, 0, 0, 0, 1, 0, 0, 0, 1. Now, so we call this the identity matrix. Okay. And what is the identity matrix for? We did an example of this earlier. James may remember. Anytime you multiply a matrix that is multipliable by that identity matrix, you're going to get the same matrix you started with. Okay? That's why we call it the identity matrix of order n. Okay? And they say exercise 67 will be that proof. So if you choose to do it, you certainly can. All right. Now, both of you have books, so I don't think I'll write this one down. But here's the theorem at the top of page, whatever that page is, 56. There is our next theorem. Okay? All right. And here's how it reads. If A is a matrix of size m by n, m rows, n columns, okay, then the properties below are true. I think I will write these out. I won't write out all the words. Oh, looky here. Here comes Ricky. Let me get her in here before I lose her here. So Ricky's here. Okay, my first class this morning, I had perfect attendance. Now, of course, that was only 6 students. So I was hoping for perfect attendance today in this class. And right now we have 3 out of 4. So if Emmanuel will just show up, we'll have perfect attendance for this one too. But it's getting a little late. But Ricky, glad you're here. Okay. Now what we're doing, we're on in Chapter 2, Matrices, Section 2.2, Properties of Matrix Operations. And we're on Theorem 2.4, the top of page 56. And Ricky, you do have a book too, right? Yay or no?
Yes.
Yes, you have a book?
Mm-hmm.
Okay, good. Okay, so I'm not going to write all of it down, but here's what I am going to write down. Okay? Where is my cursor? Come on, where did you go? Ah, there it is. Okay. Here's what I'm going to write down. A is an M by N matrix. M rows, N columns. Okay. Now, if I take that matrix A and I multiply it by an identity matrix, you tell me what size identity matrix does that have to be?
N by N.
Say again, N by N you said?
Yes, sir.
Yes, and we usually just put a single thing, N, A-N. The reason for that, this is M by N. This has to be, because it's square, and N by N. So you're absolutely right. And guess what you get as an answer? Identically the same thing. You multiplied it by A. And that will still be an M by N. Because you multiplied an M by N by an N by N, and that gives you an M by N. And it will be exactly the same values. Every element in this A is the same as every element here because the identity matrix does not change it. But if you multiply the other way, okay, you multiply identity matrix on the left by that matrix A, what size does that identity matrix have to be? Remember, A is still an M by N. So what size would this identity matrix be?
What were you saying? Multiply I by
I by A, the same A we did before, but this time we're multiplying on the left by identity matrix. What size does it have to be?
N by M.
M by M. You're absolutely right. A different identity matrix if you multiply on the left than if you multiply on the right. If A has different number, if it's A is rectangular rather than square, then your identity matrices will be different sizes depending on whether you multiply on the left. Because this is the M by M times an M by N, and that will again give you A, same A, but that's going to be an M by N because you multiply M by M by an M by N. That gives you an M by N. Just same as that did. It's just that there are different sizes on the different, depending on which side you multiply by, you have to use a different identity matrix. If it's not A is not square. Okay. Now, I'm going to clear the screen. Is that okay? All right. And let's do example 6. Here is a matrix. 3, -2. Yuck, pen quit. I don't know why it did that. I wasn't holding my finger down and it acted as if I was. Okay, I have no idea why. Okay. I am going to put a bigger thing on it. Okay. This first matrix is a 3, -2. Oh, looky here. Here comes your manual. Ding, ding, ding. Perfect attendance again. What a great Thursday, folks. Perfect attendance in my first 2 classes. Okay. 6 in the first, 4 in the second. Perfect attendance. Way to go, Jemanuel. You made it perfect attendance today in both of my classes this morning. Okay. We're in Chapter 2, Matrices, Section 2.2, Properties of Matrix Operations, and we're on top of page 56, example 6. I'm just writing it down now. Okay, and by the way, remind me, Jemanuel, do you have a book?
Yes, sir.
Yes, okay. All 4 of you have at least an ebook or PDF or something. Great, thank you. All right. Now, the first row of this first matrix is 3, -2. Okay. Second row is 4, 0. Okay, third row is negative 1, 1. Okay. Now we're going to try to multiply that by an identity matrix. What size identity matrix had that better be? What's the size of this first matrix? This one here, the one I just wrote down. Someone?
3 by 2.
3 by 2. So if you're multiplying on the right by identity matrix, what size did it better be?
3 by 2.
2 by 2, you're absolutely right. And what would be the entries in that 2 by 2? Identity matrix.
What did you say, Dr. Fowler?
The entries in an identity matrix, a 2 by 2 identity matrix.
You can have it. It's gonna be like 1 0 0. 1 should be right there.
Perfect. You got it. And we said we could multiply it. Let's see if we can. Okay. What size will you get as an answer?
3 by 2.
A 3 by 2. So that's going to have 2 columns, but 3 rows. Okay. Let's take that first entry. First row, first column, first row of the first one times the first column of the second one. 3 times 1
3
plus
-2 times 0.
which is 0. So that's just going to give you
3.
a 3. The 1, 2 entry here, first row here, second column there. That will be first row here, second column here. 3 times 0,
0.
0. Minus 2 times 1 is?
-2.
Minus 2. Hey, looks like we're duplicating it, doesn't it? Let's see the 2, 1 entry. Second row here, first column there, second row here, first column there. 4 times 1?
4.
4. Whoops, I wrote too soon, didn't I? Plus 0 times 0 is 0. So I wasn't too fast. The 2, 2 entry, second row here, second column here. 4 times 0, 0 plus 0 times 1, 0. Okay, the 3, 1 entry, third row here, first column here, -1 times 1, -1 plus 0 is -1. And the 3, 2 entry here, third row here, second column here, third row here, second column here. -1 times 0 is 0 plus 1 is 1. And guess what? You exactly replicated this here. Same matrix. If you multiply any matrix by the appropriate size square identity matrix, all identity matrices are square, you're always going to replicate that first matrix. Always, always, always. They have to be the right size. Okay? This time, excuse me, we're going to multiply a column vector or a column matrix. And that happens to be a 3 by 1. -2, 1, 4. But I'm going to multiply that on the left by an identity matrix. What size did it better be? Anybody?
1 by.
This is a 3 by 1.
Oh, I thought you said multiply on the right side.
No, on the left side.
Anything by 3.
It's got to be a 3 by 3. So you name for me the 3 by 3 identity matrix.
1.
1.
0.
0. Whoa, that's an
0.
ugly 0. 0.
0.
0. You got stuck on zeros, didn't you?
1.
1.
0,
0,
0,
0.
0.
Come on, get off of it.
1.
1, you got it. There it is. Now that first 0 is awfully ugly, so, but James made me write it ugly, okay. The way he said it, you know. All right, so let's see. That's a
Like
3 by
square
3.
now.
Huh?
I said
I'm a
zero
square.
like a
He's
square
making me
now.
a square. Yeah, okay. What size is your answer going to be?
3 by 1.
3 by 1 again. Well, that part's the same. Let's see if the rest of it is. So it has 3 by 1, so you have 3 rows, 1 column. Okay, at least that's the same as this. Let's see if the numbers turn out the same. To do the first entry, which is first row times first column, that'll be the first row here by the first column there. And that would be 1 times negative 2
Negative 2.
plus
0.
plus,
0.
which is negative 2. That part worked out okay. This is the 2, 1 entry, so it would be the second row here by the one and only column here. And what does that give you?
0 plus 1 plus 0 will be 1.
That gives you 1. Very good. And then the 3, 1 entry here is the third row here by the one and only column here. And what does that give you?
It'll give you 1.
Say again?
It'll give you 1.
Wait, will it? 0 times negative 2 is 0. 0 times 1 is 0. 1 times 4 is 4. You exactly replicated even that column vector or column matrix, whatever you want to call it, gives you exactly the same answer, as long as you multiply by an identity matrix of the right size. Well, what's the name we gave for this one? I sub.
Yeah, I sub n.
Say again?
I sub n.
I sub 2, right?
Oh, yeah.
And this one over here would be the I sub 3. That just means it's a square matrix, 3 rows, 3 columns. Square matrix, 2 rows, 2 columns. Perfect. Okay. Now, here they're coming up with a brand new concept, and they're just sort of writing it down. Okay? Now, let's say we have, now here's a new thing here. A has to be square. So I'm just going to write SQ. A has to be a square matrix. Okay? Now, what do you think we would mean if we said A to the first power? That would just be A. Just like 7 to the first power is 7. X to the first power is X. Well, why did I write it? It's supposed to be an A. Okay, my example messed me up. Okay, A to the first power means that. What do you think we could possibly mean by A to the second power? Here's what we mean. A times A. Just like we do in real numbers. 7 squared is 7 times 7. Negative 3 squared is negative 3 times negative 3. Anything squared is multiplied by itself. Same true with matrices. However, they've got to be square matrices or you can't even do it. If this was a 2 by 3 matrix or a 3 by 2 matrix like this one, you can't multiply it by itself because that would be a 3 by 2 by a 3 by 2. They don't even multiply. So as long as A is square, you can do this. So A to the, ooh, that's an ugly A, isn't it? A to the kth power, where K is some integer, positive integer, that would be A times A times A times dot, 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 until you had KA's down there. K factors of A. A is a factor K times. That's what we mean by raising a matrix to a power. Now, let's take it one more step, but let's go backward this time. What do you think we would mean by A to the 0th power? Any idea?
1.
Okay. In matrices, what stands for 1?
I think I forgot.
The identity matrix.
Oh.
So that would be the identity matrix of the same size as A. So you're right. In numbers, that would be 1. In matrices, it would be the I matrix of the same size that the A was. Okay? Now, with those things in mind, let's come up with a few rules. What if this K down here was made up of, we got 3 of them here, so let's call this one A cubed. And let's just imagine, give me a number for K. Just make sure it's greater than 3. Give me a number. 5? So if this K was 5, then that would be A3 times A what? Squared. Just like numbers. If you're multiplying 2 cubed, 8, times 2 squared, 4. 8 times 4 is 32. Isn't 32 2 to the 5th power?
Yes, sir.
Yes, it is. Same thing for matrices. So in general, the rule would be if you're multiplying A to the jth, and they make them little j's, I think, yeah. The jth power of A, multiply that by the kth power of A, you're going to get A to the what power?
J plus K.
J plus K, you got it. Perfect. J plus K. Just like it is for real numbers. Okay? All right. Multiplying two same bases, different exponents, keep the base, add the exponents. Same thing works with matrices. Now, what about this one? What if you have A raised to the jth power and you take that and raise it to the kth power? Uh-oh, SpaghettiOs. What would that be?
I think it would be AJ, and it'll keep going.
To the kth power. You multiply the exponents. Because think about what this means. Give me a number for J. Any number.
2.
6, you said? Okay. All right. Give me a number for K.
2.
2. Okay, I like that better. Okay. So A to the 6th power would be A times A times A times A times A times 6 A's, right?
Yes, sir.
And if you're squaring that, you multiply 6 A's times 6 A's. So if this is, where's my cursor? There it is. Okay. If this is A to the 6 times A to the 6, that would be A to the 6 plus 6 is 12. Well, isn't that the same as 6 times 2 is 12?
Yes, sir.
Yes. So when you're raising a power to a power, you multiply the exponents. Now, back when I teach algebra, I say it this way. I look at our operations sort of in hierarchies. I put adding and subtraction at the lowest level, multiplication and division at the next level, and then powers and roots at the next level. Okay? When you're dealing with exponents, okay, if you're multiplying the bases, you're adding the exponents. The exponents always step down one level. If you're raising an exponent to an exponent, that's your powers, you step down and you multiply the exponents. I don't know if that's helpful. To me, that sort of makes sense. It may not make mathematical sense, but to me, it makes sense. Okay. So anyway, that's the rules that we have. Now, remember here, in all these, J's and K's can only be positive integers. Now, they could be zeros, so I take that back. The book says positive integers. No, the book says non-negative integers, so that allows for a zero. But there is no way, we have not defined what a to a negative number is. In fact, it doesn't. I don't want to say it doesn't exist, but for now, I's and J's and K's can only be non-negative integers. No fractions, no 1/2. You can have those with exponents, okay? You can have negative exponents. But with matrices, we're going to keep them positive integers or zero, okay? Non-negative integers. All right, so let's do example 7. Okay. How are we doing on time? Oh, here it is on the thing. 12:24, we go to 1:15. So we've got another about 45, 50 minutes or so. Okay. So let's do example 7. Here's a matrix A. Somewhere here. There it is. Okay, here's matrix A. Now, it has to be square for all these things that we're just talking about to work. So let's make it a square matrix, and let's keep it as simple as we can, a 2 by 2. So that would be 2, -1, 3, 0. That may not be as simple as we can, but it's simple enough, okay? Of course, 1 by 1 would be really simple, but that's not very interesting. And identity would be simple, but that's not very interesting. So let's do this. So the first thing we're going to do is figure out what a cubed is. Okay? A raised to the 3rd power. Anyone want to make a guess of what that means?
8 times A times A.
A times A times A. You got it. So that will be 2, -1, 3, 0, times 2, -1, 3, 0, times, it's sort of old, isn't it? I'm glad they didn't say 6 like James did, okay? That would be a 2, -1, 3, 0. Now remember, multiplication of matrices is associative. It's not commutative, okay? So we can do them any order we want. Let's just do the first 2 and see what we get. You certainly can multiply them. They're the same sizes, and that's going to give you a 2 by 2. So let's get that. Kind of crooked, but we got it. So the 1 entry will be the first row here by the first column there. So that's going to be 2 times 2 is 4 minus 3, 1. Agreed?
Yes, sir.
The 1, 2 entry here will be first row here, second column here. So it'll be 2 times -1 is negative 2 plus 0, so that's going to be negative 2. Ooh, ugly, isn't it? Okay, the 2, 1 entry here is going to be second row here, first column here, and that would be a 6 plus 0 is 6. I like it when there's zeros in there. It makes it easy, doesn't it? And then the 2, 2 entry here will be second row here by second column here, and that would be a negative 3 plus 0 is a negative 3. It's kind of ugly writing. It's very ugly writing. But anyway, we're going to multiply that by a again, which is 2 minus 1, 3, 0. All right, boy, hunger is setting in, folks. Okay, 45 minutes. Let's make it. All right. I should have had another package of almonds. Okay. In fact, let me get a swig of something here. Oh, man. All right. Now, of course, a 2 by 2 times a 2 by 2 is going to give us a 2 by 2. It's going to be 2 columns and 2 rows. Okay. All right. The 1, 1 entry here is going to be first row here, first column there. If you can read my ugly writing, let's go for it. 1 times 2 is 2. And then you got a minus 2 times 3 is a negative 6. So I think that comes out to be a negative 4. That was a bit too long of minus sign. Say again?
Yes, sir.
Okay. The 1, 2 entry here will be first row again by the second column here, and that's going to be a minus 1, isn't it? Got it? Yay or nay?
Yes, sir.
Okay. Then the 2, 1 entry here is going to be second row here, first column here. Ooh, okay. That's going to be 12 minus 9. That's going to be 3, I believe. Right?
Yes, sir.
And then the 2, 2 entry, second row, second column, I think is just going to be a negative 6. Agreed?
Yes, sir.
All right, I think we just did what they asked, okay? That gave us negative 4, negative 1, 3, negative 6. Yes. Is there anything special you can look at that and tell it was a cube? Nope, not a thing. Okay? This just showed you how you can do those. Okay? Now, my mom's mom, I did know her a little bit. She died when I was fairly young. Her name was Nora, which is not a very common name now, but all of her friends and relatives called her Nori. And evidently my mom's mom could get off onto a story and just not let it go. And she had an aunt who was not that much older than her, but a little bit older than her, called Aunt Net. And they liked to sit and talk sometime, but after a while, if my grandmother got onto it, and I've been told this, I never watched it, but my mother told me the story. If my grandmother got off into this one story and just kept going and going and going, Aunt Net would say, Nori, let's just jump another rabbit. Okay, well, we're going to jump another rabbit here. We just talked about raising a matrix to a power. All of a sudden, we're jumping back to number of solutions for a linear system. Haven't we already jumped this rabbit before? Yeah, we have. Well, here's a theorem. You all got books. I'm not going to write it down for you. For a system of linear equations, precisely one of these statements is true, and only one. That system of equations either has one unique solution, exactly one unique solution, or it has infinitely many solutions, or it has no solutions. Okay? We've been there. We've done that. Why are they bringing this up again? But they're now stating it not as just a statement, but as a theorem. And they have a little proof at the bottom, and that takes a while to do, but I'll let you take a look at it and read through. Now, I think I've asked this before. Are any of you math majors? All of you engineers? I think you are, aren't you? Okay. If you're a math major, almost certainly you probably need to go through the proof. I think the engineers just say, hey, just tell me what it is and we'll work with it. Okay, is that right?
Yes, sir.
That's how I do it. I'm a physicist. I'm not an engineer, but boy, just tell me what the rule is. I'll follow it. Okay. So they do that, do a little proof, and guess what they do? They jump another rabbit. Okay. They go to something else. This is a new thing, and this is called the transpose of a matrix. And here's what the transpose of a matrix. Let's define it first, and then we'll do the little discovery in the margin. The transpose of a matrix is formed by writing its rows as the columns. Okay? So, let's say we have this M by N matrix A. So I'm going to clear the screen here. Can I do that okay with no objections? This is jumping another rabbit here. Okay? Here is your matrix A in generic form. Sort of a crooked A that time, isn't it? Okay? In generic form, this matrix A would be, we usually name the elements the same letter but lowercase. So that would be little a, 1, 1, meaning it's first row, first column. Little a, 1, 2, first row, second column. Little a, 1, 3, first row, third column. And we'll just dot, dot, dot that until we get out to a sub 1 n. Because we said that A was an M by N matrix. I didn't write it down. Let me write it here. An M by N matrix. They did the by. I didn't have room, so I just said MN. Okay? So, there are N columns, so you go 1, 2, 3, 4, 5 up to N. Okay. The next row, because it's a row, that would be A sub 2. Second row, first column, A sub 2, 1. The next one would be A sub 2, 2, because it's second row, second column. And then the next entry would be A sub 2, 3, because it's second row, but third column. And then this keeps going dot, 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 until it gets out here to A sub still 2, second row, but the nth column, the last column end, or n columns. The next row would be A sub 3, 1, because it's third row, first column. A sub 3, 2. My 3's aren't very good as about anything. The A wasn't very good. Third row, second column. A sub 3, 3, third row, third column, and we'll dot, dot, dot that up until you get to the A sub 3n, third row, nth column. And at this point, we'll just dot, dot, dot down below as well until we finally get to the A sub m, because you have m rows, but first column, 1. This will be A sub M2. And this one would be A sub M3, because it's mth row, third column, and then we'll dot, dot, dot that over till finally we have the A sub mth row, nth column, A sub Mn. So you have a dot, dot, dot here. You have a dot, dot, dot there. A dot, dot, dot there. A dot, dot, dot everywhere. Okay. Okay. All of them are dotted, dot, dot, dot. That's your A. Now, what did we say the transpose was? It's exchanging the rows and columns. So this would then be what we call A transpose. And its superscript is T. Now that's not representing any number. That's a letter, T, transpose. Now, what size would A transpose be? Anybody? If you're exchanging rows and columns, it would be an
N by M.
N by M. You're absolutely right, if I could write it. Okay? And here would be the elements. Okay? You're exchanging the rows and columns. So the first element is still going to be A11. But the second one is now going to be what was your A21, because you exchanged the rows and columns. This was 1, 2. This, now it becomes 2, 1. This becomes A sub 3, 1. And then you have a dot, dot, dot until you get up to A sub M. That's how many rows you got now. 1. Okay? These are the same elements as before, but in different locations. Okay? This one would then be exchanging rows and column. That would be A sub 1, 2. Exchange the rows and column. This would be A sub 2, 2. Notice what elements don't move. Your diagonal elements, because they have the main diagonal elements. Okay, now this isn't a square matrix, so you're going to run out one way or another down here. But all those that are on that main diagonal, they stay the same. This would then be an A sub 3, 2. And this would dot, dot, dot out to A sub M2. Okay, and then this will be an A sub 1, 3, exchange rows and column, A sub 2, 3, exchange rows and column. This would be your A sub 3, 3. That didn't move. It's still in the same place it was before because it's on the diagonal, main diagonal. And these dot, dot, dot on across to A sub M3. I'm so dry. All right. At this point, we'll some dot, dot, dot down the page here until we get to A sub 1N. We exchange the rows and column, and we'll dot, dot this one down until we get to A sub 2N. Exchange rows and column, and we'll dot, dot, dot this one down to A sub 3N. And then we'll dot, dot this on across to A sub N M. No. I put these in wrong, didn't I? No? Yeah. Okay. Yeah, it's still MN. Okay. I was going to say, it seems like that should be reversed. A sub N.
Yeah, shouldn't it be A sub NM?
That's what I was thinking, but that's not what we have up above. We have the M's first here and the N's second here. And it does. In the book, you'll see it does, because the last entry, just like the first entry is 1, 1, the last entry, you're right. It still seems like that should be Oh, but okay. It is there were M rows here and N columns here. Here you have in M columns, but you're still yeah, we've got it right. The row number comes second, okay? But now we have see that okay. What we're crossing up is how we name them and what they actually are, okay? How we name what they actually are. This last entry here is still the last entry there. It was down here, it was in the nth row and the nth column. Down here, it's in the nth row and the nth column, but we still put, you see, we've exchanged, because you exchange rows and column, we exchanged how we named them, but the entry is still the same. This is entry 11, 22, 33. This is entry 21. It was down here before, but it's still the same entry. Okay? So we don't change, we keep the name of the entry the same. 21 here is the same as 21 there. It's just that this is in the first row, second column. This is in the second row, first column, but it's the same value, okay? So that's why we keep the subscript the same. And this MN is indeed right because it's the last, you see, the M here is measuring which column you are now. The N here is measuring which row you are now. So they're just backwards in where they're doing is still the MN. Nth column, N row, because you reverse. Okay. That's A transpose. Okay. Now, let's do an exercise. Okay, no, let's go back and do the discovery. Okay? Now, the discoveries sometimes are very simple, seeming anyway. I can't find my cursor. Does anyone see it moving around here? It's been hiding on me a lot today.
It's like down toward.
Oh, there it is. I see it now. Okay, thank you. Okay. All right. So it says find the transpose of each matrix. First matrix is, it is a matrix, but it's called a column matrix, which could also be called a column vector. And it's 2, 8. Okay, that's supposed to be an 8. What would be a transpose? What size would it be?
1 by 2.
1 by 2. And what would be the entries?
2, 8.
2, 8. Okay. Now this is sort of doing what we did before. That 1, 1 entry is still the 1, 1 entry, and the MN entry here was the NM entry here. They're the same entry. So you had to name them the same thing. Okay. Absolutely right. Got it right. Let's do the B part. Here is matrix B. A little bit bigger matrix than we had before. This is a very creative matrix too. A lot of thought was put into these. It's 1, 2, 3, 4, 5, 6. I think James came up with this one. Okay,
Probably
7. Say again.
Probably so.
Okay, 8. He probably could write better than this, though. 9. Okay, it's not that funny. Okay. Now, what is B transpose? What size will it be? That's supposed to be a B. It doesn't look like it. It's supposed to be a B. What size will it
Still
be?
be a 3x3, right?
Still be a 3x3, but call out the entries to me.
1,
1,
4,
4, you're absolutely right.
7,
7,
2,
2,
5,
5,
8,
8. He's calling them out too fast. Okay. Trying to emphasize how slow I am. Okay, go on.
3,
3,
6,
6,
9.
9. Hey, good speed. Okay. That's it. There's B transpose. That's an ugly B, but it's B transpose. Now, matrix C is also a 3x3. Okay, and it happens to be 1, 2, 0, 2, 1, 0, and oh wait! I've just realized something. We didn't do the discovery. I don't know what went wrong with my brain. 0, 0, 1. Okay, we've got to go back and do the discovery, but we'll do these first. Let's first give me what C transpose is. Okay, someone call it out to me. Say again? Okay, it's sort of garbled. Could you say it a little louder?
I said, I thought somebody else was going to do it.
Okay.
So you got 1,
1,
2,
2,
0.
0. Hey, I didn't say give me C. I say give me C transpose.
I'm just trying.
Okay, what's next?
2,
2,
1,
1.
0.
Were you paying attention? I say give me C transpose.
0,
0,
0,
0,
1.
1. I think he gave me the same matrix, don't you? He did, but that is C transpose. This is a special name. This is called a symmetric matrix. The definition for a symmetric matrix is one who's equal to its transpose. In other words, its columns and corresponding rows are identical. So he was absolutely right. This is the C transpose, but this happens to be a symmetric matrix. Same rows as columns. Okay? Now let's do D. And then we'll come back and do the other. Here is D. D is 0, 1, 2, 4, 1, negative 1. Okay, what's D transpose? What size will it be?
3 by 2.
3 by, wait, what did you say? 2 by 3? Say yes.
Yes.
All right, good. A 2 by 3. And what will be its entries? I'll get it started. 0,
2,
2,
1,
1,
1,
1,
4,
4,
negative
-1. Perfect. Perfect. And you see on every one of these how the first entry and last entry are always the same. First entry, last entry, always the same. First entry, last entry, always the same. They're in different locations, but they are the same. And that's why it did come out AMN, AMN. Had to be. Wasn't the row number, the row column number anymore. Okay. Now, let's back up one and do we have time? Yeah, I think we do. Let's do the discovery. I forgot to do it. Here's A. I kept saying we were going to do it, and then I went right past it. And you let me do it. It was all James's fault. Okay. Here's matrix A. 1, 2, 3, 4. Yeah, he did it. Okay. 1, 2, 3, 4. Very creative matrix there. Okay, there's matrix A. Now, here's matrix B. Three, 5, 1, -1. Okay. Now, the first thing it says to do is, I'm going to break it down in little pieces. Let's first do AB. Come on. Anyone seen the cursor? There it is. Okay. Let's first do AB. A, B. I wish I'd have written them side by side rather than up. I did like the book did, but it's sort of dumb. Okay, obviously it's a 2 by 2 because they're both 2 by 2s. Okay. All right. 1 entry here will be first row of A by first column of B. What would that be?
5.
5. Perfect. Okay. Next entry, first row of A by second column of B, row, column. And what would that be?
3.
3. Excellent. Okay. And the next entry with a 2, 1 will be second row of A, first column of B. That would be
13.
Okay, wow, fast. That'd be 9. Yeah, plus 4 is 13. I'm slowing down because I'm so hungry. Okay. That's my excuse anyway. Okay, and the second row, second column, second row here, second column there. That would be 11. Very good. I think he worked it ahead of time, didn't he? Okay. But they didn't really ask for what AB was. I broke it into smaller pieces. First thing they said to get was AB transpose. So what would be AB transpose? Now, that, by the way, is written with AB in parentheses, and that's why I did the multiplication first, and then we're going to transpose it after we multiply. So that's what is next, so you tell me what that is going to be.
2 by 2.
A little louder?
It was a 2 by 2, and it's going to be
Okay.
5,
5,
13,
13,
3,
3,
and 11.
and 11. Okay, that part's done. The next thing we wanted to do was A transpose times B transpose. So let's up here write what in the world A transpose is. Also going to be a 2 by 2. What will A transpose be?
1,
1,
3,
3,
2,
2,
4.
4. And they also want to know what B transpose is. Also going to be a 2 by 2. Whoa! And what will it be? 3,
1,
1,
5,
5,
negative.
-1. All right, and then the next thing we want to know is what's the product of those two? A transpose times B transpose. You want to hazard a guess? Or you want to work it out?
I wish it would be the same as the other one, but it isn't.
No, it isn't, is it? Okay, so let's work it out. It's be a 2 by 2, of course.
Yes, sir.
And it would be, the 1-1 entry would be first row here by first column there. And that would be
1 and 3 be 3.
3,
And 3 and 5 is 15. So it'd be 18.
18. Got it. Okay. The 1-2 entry here would be first row of A, second column of B, and that would be
1 and 1 is 1. Minus 3 would be -2.
-2. Perfect. Okay. The 2-1 entry here would be second row of A, first column of B. That would be
2 and 3 is 6. 4 and 5 is 20, so it'd be 26.
26. Big old number. Whoops, that's an ugly 6 though. Okay. And then the 2-2 entry would be second row of A, second column of B.
2 and 1 is 2. 4 and 1, 2 minus 4 would be -2.
-2. You're absolutely right. It's sure not the same as AB transpose, is it? It's nowhere close. Okay? But they said try this one on for size. Okay? Now, I almost figure I have to, I'm going to do it this way. Yuck. Come on. Okay, here it is. I'm going to write down A transpose again. I'm going to write it here. How are we doing on time? Oh, yeah, we got time. Okay. A transpose, you tell me, well, I mean, it's just right up there. So it's 1, 3, 2, 4. Okay. Now, what we're doing down here is A transpose. No, B transpose. Notice how that became a B transpose. Okay. A transpose. It's just getting worse and worse. Okay, so we're going to use those two up here to do it. Again, it's a 2 by 2, of course. Oh, but that's way too big. All right, I'm getting tired. Okay, so it's going to be a 2 by 2. All right, goodness gracious. Let's do it. First row, first column here will be first row here, first column there. That would be
3 and 1 is 30.
1
and 2 is 2. 3 and 2 is 5.
5. Okay. And the 1-2 entry here will be first row of B transpose again by the second column of A transpose. And that would be
3 and 3 is 9. 1 and 4 is 9 plus 4 is 13.
13. Okay. And then the 2-1 entry here will be second row of B transpose times first column of A transpose. And that would be
5 and 1 is 1, minus 2 is 3.
3. Excellent. And the 2-2 entry here would be second row of B transpose times second column of A transpose. And that would be
5 and 3 is 15, minus 4 is 11.
11. Ding, ding, ding. Look at that. AB transpose looks like it's the same as B transpose A transpose. Okay? It says make a conjecture. Yeah, when you transpose the product of two matrices, you reverse the order of the product of their transposes. Okay, that's my conjecture, and I think it works. Okay, so let's look at the theorem 2.6 at the bottom of the page and see if that holds true. Okay, now, if A and B are two matrices with sizes such that the matrix operations are defined, so they got to be the appropriate sizes, C is a scalar, okay, any old scalar. Then here are the properties, of transposes. If you take A and transpose it, and then transpose it, you go back with A again, right? You reverse the rows and columns, and then reverse the columns and rows, you're back where you started from. So that gives you A. So the transpose of A transpose is A. Make sense? Now, when you're adding two matrices, as long as they're the right sizes, in other words, A and B have to be the same sizes, and then you take that sum and transpose it, now you reverse the rows and columns, so whatever sizes you had before, like M by N plus M by M is going to be M by N, but transpose it, you get it N by M, okay? Well, if you transpose A, you had an N by M, add that to B transpose, which is N by M, and you still get an N by M, and guess what? It's the same as so the sum, the transpose of a sum is the sum of its transposes. That works. Doesn't work with products, not quite. Here's the third one. A scalar times A, transpose that, and you get the scalar times A transpose. The scalar just comes outside and you transpose away however you want to. Doesn't matter. The transpose of a scalar product is a scalar of the transpose. Okay. And then 4. This is the one we just did. The transpose of a product of two matrices is the reverse product of their transposes. Okay? You multiply the two transposes together, but in reverse order. Okay. So that's your theorem 2.6. All right. Let's see if we can do example 9. Now, example 9 you can also find at larsonlinearalgebra.com and for an interactive version of this type of example. So let me clear the screen. Oh my goodness. I don't know. I guess it's Thursday and I'm just running out of steam. I can't stop yawning. Sorry. Okay. Now, here are two matrices. We may not have time to finish this, but let's give it a shot. Here's matrix A. I may not even have time to write it, okay? We got 8 minutes. Let's see if I can get it written in 8 minutes. Here's matrix A, a big old 3 by 3. 2, 1, negative 2. Negative 1, 0, 3. A 0, negative 2, 1. Here's matrix B. It's a 3 by 2. That's 3, 1. 2, -1. And a 3, 0. Now, the first thing they ask us to do is do the product of these two, sort of like we did with the discovery, only these are bigger, okay? So we're going to come up with A times B. Okay, so let's do that. What size is that going to be?
Three by 2.
3 by 2, you're absolutely right. Okay, so it's going to be a blank, blank, a blank, blank, and a blank, blank. Okay, now, first entry will be 1, 1, so it'll be the first row of A by first column of B. What would that give you?
3 times 2 is 6. 6 plus 2 minus 6 is 2.
2. Excellent. Okay, the 1, 2 entry here would be the first row of A again, this time by the second column of B. And that would give you a
1.
1. Look at that, how fast. Okay. Now, the 2, 1 entry would be second row of A by the first column of B, and that would be
3.
so
Negative 3.
Yeah.
Plus 9 would be positive 6.
Positive 6. Excellent. And then the 2, 2 entry would be second row of A again, this time by the second column of B, and that would be
-1.
-1, and that's all, folks. Okay. Now, the 3, 2 entry here would be the third row of A, 3, 1 entry by the first column of B, and that would be
-1.
-1 again. He's quick. Okay. And then the 3, 2 entry would be third row of A, second column of B.
2.
2. Okay. Very good. The next thing they want us to do is to transpose it. So what's AB transpose?
It's going to be a 3 by 2. I mean, a 2 by 3.
2 by 3, right. All right, and what would they be?
2.
2,
6.
6,
-1.
-1.
1.
1,
-1.
-1,
2.
2. Okay, there's AB transpose. Now they want us to calculate what B transpose A transpose is. So let's first do what B transpose is. B transpose. What size will it be?
2 by 3.
2 by 3. And what would it be?
3.
3,
2.
2,
3.
3,
1.
1. Oh, goodness gracious, look at that. That's a negative sign. That's a mighty big negative sign. Okay. That's a -1, right?
Yes, sir.
Why you got it so wrong, I don't know. Look at that. It's just drawing wherever it wants to. Okay. Okay, we'll try it again. Goodness gracious. Look at that. I'm not doing that. It's throwing it in there where I think it's getting tired too. It's gone without lunch. Okay. All right, let me see if I can get it to do this time. -1, wasn't it? -1. Okay, finally, and then a 0. Wow, I didn't expect that. Okay, we want A transpose as well. What size will that be?
3 by 3.
That's the same old 3 by 3 size. All right, and call them out to me.
2.
2.
-1.
Yeah, -1.
0.
0.
1.
1.
0.
0.
-2.
-2.
-2.
-2 again. You're stuck on it, aren't you? Okay.
3.
3.
1.
1. All right. Now let's do B transpose, A transpose, the product of those two. B transpose, A transpose. See, the discovery had to do an extra step in there. This is not. It's saying go for what we just said it was, and let's see if it's true. Well, what's the size of a B transpose, A transpose?
2 by 3.
2 by 3. Which is encouraging because that's what the other was. So let's see what we get. 2 by 3. 3 columns, 2 rows. Whew. Goodness gracious. All right. 1 entry here, first row here, first column there. If you can read my ugly writing. Okay, what would it be? That is a 2, by the way. I was thinking it was a 3, but that's a 2. Okay, so what's that?
2.
The total is 2?
Yes, sir.
Yeah, it's 6 plus 2 minus 6. Yeah, 2. Okay, next.
-3 minus 0. -3 plus 9 would be -6.
-6. Or, no, positive 6.
Positive 6.
Right.
Yes, sir.
Okay. I'm going to be really cheap. I'm just going to make that a plus 6. Okay. All right, next.
-4 plus 3 would be -1.
-1. Good so far. Next. Remember that is a 2 up there.
1, that's 2. Minus 1 is 1. So it's -1. I mean, that's 1.
1. Okay, good. Next.
1 is -1.
That's all.
So it's -1.
Whoa! It did it again. Just takes off and does whatever it wants to. Okay. Let me try it one more time. All right. -1. -1. Got it. And now that last one. The one we've been waiting for.
2.
2. You got it. And that's exactly what we got there. Yes, sirree, Bob. Or James, or Aaliyah, whoever. Okay. It's 2, 6, -1, 1, -1, 2. Exactly the same. They are equal. And we went 2 minutes over, but guess what? I won't charge you any extra today. Okay? So we'll begin next time with example 10. We almost finished this set 2.2. Homework exercises here would be any of the odds 1 through 5. They're all at Calc Chat. Any of the odds 7 through 11, they should all be at Calc Chat. 13 should be at Calc Chat. Any of the odds 15 to 21 should be at Calc Chat. 23 should be at Calc Chat. 25 should be at Calc Chat. 27 should be at Calc Chat. 29 should be at Calc Chat. Any of the odds 31 to 35 should be at Calc Chat. 37 should be at Calc Chat. 39 should be at Calc Chat. 41 or 43 should be at Calc Chat. 45 should be, or 47 should be at Calc Chat. They think you need extra device for 47. Try it on your own, whatever. 49 or 51 should be at Calc Chat. 53 should be at Calc Chat. Now that's sort of an interesting one there, because they're now talking about the nth root of a matrix, which, anyway, I'll let you work on that. 55 is a true false. It should be at Calc Chat. 57 should be at Calc Chat. '59 should be at Calc Chat, I think. Yeah, I mean, I know it should be. Then you get into some proofs. And you can do as many or as few of these as you'd like. Any of the odds 61 through 69. Okay? Then 71 or 73. Now here they come up with a brand new definition. We already knew what symmetric matrix is, but they came up with a skew symmetric matrix. Okay? So you have to look at that. Then you can do either 75 or 77. They should be at Calc Chat. And then you can hold off or do 79. That's up to you. Okay. I sure didn't see a whole lot of transposes in there. I must have missed them. Did you see many? Well, anyway, we'll pick up next time with example 10 on page 59. Any questions? All right. Two more things. Number one, have a good and safe weekend. And number two, doing linear algebra will make it good and probably pretty safe too. Don't you think? All right. Don't forget your papers either, research paper. All right, good deal. If there are no last questions, I'll stop the sharing.
When is our research papers due for this class?
Okay, same as before. They're due by the last day of class, which will be the last. Seems like we meet. I don't remember what the last day of a Tuesday, Thursday class. I think it's a Tuesday. I believe it is. And yeah, the Monday, Wednesday classes are Monday, and Tuesday, Thursday, I think are Tuesday. Whatever the last day of class is, not the final day, final exam day, but the last day of class. But please, please, please try to get them in earlier. And if you get them in the month of June, you still get a bonus point. In July, there is no bonus point. So if you can, sooner is better than later, okay? Helps me spread my grading over time too, okay? All right, any other questions? Great question, by the way. All right, I'm going to stop the sharing, and we'll stop the recording, ending the meeting for all. And I'll turn around and stop the